Hi, I'm Nick Eliadis of Achronix Semiconductor, and I'm here today to talk to you about how Achronix is enabling the ODSA chiplet roadmap. I am the Senior Director of Product Planning here at Achronix Semiconductor. We are part of the open community, and this presentation is part of the server track. So who is Achronix? We are the only independent high-end FPGA provider in the market today. We were founded over 17 years ago in 2004. We are headquartered in Santa Clara, California. Key markets we address are artificial intelligence, machine learning, SmartNIC and other networking related solutions, storage, automotive, and 5G infrastructure. The key products that we offer today are high-end FPGAs, as well as embedded FPGA technology. Embedded FPGA technology is IP that is used within a customer's device. I'll talk a little bit more about that in a couple of slides. We have over 1,000 man-years of R&D in our products. We are the recipient of many awards and have key partners across the semiconductor industry. So today there is a need for data acceleration solutions. Moore's Law, which growth doubles every 2 years, and which traditional program computer CPU architectures kind of track, is only been doubling every 2 years, and there is a need for greater growth. AI is growing, doubling every 3 to 4 months. There has been a 300,000 time increase since 2002. So if there are not solutions that provide benefits around performance, power efficiency, and cost and flexibility, this is not a sustainable growth. And today we feel that FPGA technology does address those three limitations: the performance, power efficiency, and the cost of flexibility. So let's talk about Achronix's products. We have high-end FPGAs, as I said earlier. Our Speedster 7T family is one of the most advanced high-performance FPGAs in the market today. It is optimized for data acceleration. It is has over 2,500 machine learning processors that are configurable with many different number formats for machine learning inference. We have advanced on-chip transports in the form of a 2D NOC that allows you to move data around the FPGA fabric very efficiently. And this technology becomes the architecture for embedded FPGA technology and chiplets. So the embedded FPGA technology, we call it SpeedCore. It basically is a hardened FPGA block that can be put into a customer's ASIC or SoC design to enable FPGA programmability within that device without having to have an outside, a standalone FPGA. It provides a lot of flexibility in their products. We've been providing this IP for many years, and we've shipped over 10 million of our cores into customers' products. And finally, we have accelerator cards. Our vector path card is really a mechanism by which customers can basically develop with a Speedster 7T, deploy it in a data center in a PCIe form factor. It comes with a full suite of software, and it's supported by Bitware and our partners Dell and HP. Now, all this is supported by our ACE design tools. Our ACE design tools provide synthesis, verification, timing, place and route, programming, and debug. So it's a full end-to-end tool suite to go from idea, concept to a working FPGA design. So chiplets and how embedded FPGA technology can enable chiplets. In the far left here, we have a traditional embedded FPGA that our customer would take, build their ASIC, and then embed our FPGA technology in their ASIC to provide flexibility And then, this ASIC can be reused in maybe potential different applications by reprogramming that FPGA fabric. But that provides one device with programmability. If our customer then wants to have this flexibility across a family of products in different scales, we can work with them to develop a FPGA chiplets. That's basically our speed core FPGA technology with a die-to-die or package-to-package interface on it that allows it to interface to an ASIC or SoC. And what this gives our customers, now this can be, can be on an interposer, silicon interposer, it could be on an organic substrate, or it could be on a PC board. But what this gives our customers is the ability to not only deploy a single device with flexibility by putting these two together, but then other members of other ASICs or future ASICs, or ASICs that are smaller, bigger, can use this, let's say, off-board or sidecar FPGA to basically provide the same flexibility that they had in this embedded FPGA, but now it is accessible through a die-to-die or a package-to-package interface that then provides that flexibility across numerous devices in their product portfolio. And then finally, we can do a similar thing where now the chiplet has taken on even more capabilities. And what in terms of domain IP, what I'm referring to here is interfaces for I/O like Ethernet or PCIe, or memory interfaces. And what this allows the chiplet to do is precondition data as it comes in and out of the system before it is accessed by the ASIC or SoC. So not only does it provide the flexibility through the die-to-die interface for accessing the embedded FPGA speed core technology, but it also gives you the ability to bring data in, process it through the speed core, and then present it to the ASIC or SoC. So that it becomes a more capable chiplet that's not just a sidecar FPGA, but it's a sidecar FPGA plus I/O and memory subsystems. So here's two chiplet use cases that will highlight this capability. On the left, you would have a domain IP ASIC, maybe a 5G base station or some sort of a network device that's providing some sort of capabilities, deep packet inspection, or some sort of other ASIC that's purpose-built for a certain type of application. The FPGA chiplet through the die-to-die interface would then provide that, as I said earlier, that sidecar capability. And then if you wanted to bring external network interface options or external memory to that chiplet, you could also do that as well. So this would be the case that you have a device that's designed for a specific use case. And then in a multi-core CPU, this would be the heterogeneous computing use case, where you have a general purpose processor or processors that then would use the FPGA chiplet as an acceleration sidecar. Again, we would have the ability to bring external network interfaces in if so desired, or attach external memory. Now, what are these die-to-die or even package-to-package interfaces? Today, ODSA has really shown that interface I/O technology such as PCIe and Ethernet could be used for connecting die-to-die. But if you want to get down to a higher performance and, let's say, more power efficient, there are XSR SerDes with AXI interfaces. There's a bunch of wires, which is ODSA is standardizing today, and then HBI, which is also a sister protocol that's being standardized in conjunction with ODSA. So these provide numerous different types of interfaces that can be instantiated here, depending on performance, packaging technology, reach, how far you want to have these devices away from each other. So those are that's two chiplet use cases that can be realized. Looking at the Achronix product family, today we have our 17500 and 1550, roughly 700,000 LUTs. There's 7800, which is a smaller version of the device with 380,000 LUTs, and then there's 1300, which is about double the size of that, and and even larger in the 6,000. These all come, some with cryptography built in. Others have our MLP, which is our math learning processor, and different configurations based upon the machine learning workloads that they have to support. Different memory configurations. Our teraops rating for the devices across here. The number of our 112 gig SerDes that are populated on the devices is anywhere from 24 to 64, 32 in the 1500. We have the external memory, DDR and GDDR6, PCIe Express interfaces. In the case of the 1500, it's got two complexes, 1x8, 1x16. The 3000 and 6000 have 2 16ths, and the 800 has 1x16. Different configurations of Ethernet from 8 all the way to 32 lanes, and our on-chip 2D NOC that I mentioned at the beginning, which provides let's say, a superhighway matrix of connections across the entire FPGA fabric, anywhere from 12 terabits per second of aggregate throughput all the way up to 48 terabits per second of aggregate throughput. So it's a very rich family of products that Achronix will be offering. So with that, I'd like to thank you for listening to this presentation. As a call for action, you can visit the Achronix website that's shown here. You can go to the project wiki for the ODSA to see all the different meetings and subgroups that are part of that, and then the mailing list that you can subscribe to if you want to be made aware of what's going on with respect to the meetings. Thank you very much, and have a great day.